have the solution in my head.
I'm glad.
I have to put it into a calculator.
Okay, guys. So we're going to talk about the dot product. That's something from a long time ago that's pretty easy. This time we're going to think of vector u as being in Rn and vector v as being in Rn. Okay? Well, obviously we cannot take those and multiply them because they have the same dimension as far as, we can't do this. We can't do like matrix multiplication. This is no good. All right? So we define this thing called the inner product. Well, the inner product is really just the dot product, and it's defined like this. So it's U transpose times V. That way we really can treat them as matrices. Okay? This thing is called the inner product. It does get a hat. Thank you. Very good. U transpose gets a hat. So U transpose V is called the inner product of U and V, and it's often written as just U dot V. This is also called the dot product. So this is the same thing that we've studied ever since the beginning of multivariable. It's just that now we're using this notation because that's going to be used, of course, later on with matrices. Later on with some of the stuff that we do with the ultimate goal is to get to this things called the least squares solution, which is where we try and approximate solutions to a non-solvable linear system. That's the goal. But this lesson is just lots of review. Okay, so here are the properties. U, V, and W are vectors, and C is a scalar. The first one is that dot products are commutative. Learned that a long time ago. Pretty straightforward. The next one is that the sum of vectors dotted with another one is the dot product of the first two vectors and the dot product of the second two vectors. Distributive. Yep, dot product is distributive. The third one is that a scalar times a vector dotted with another vector is the same as the scalar pulled out times the dot product, which is also the same as the first vector dotted with the scalar of the second. So you can associate the scalar wherever you want in that set. The last one is that u dot u is always greater than or equal to 0, and u dot u is 0 if and only if u is the 0 vector. So we combine all of those rules to write one that's a little more useful for the work that we're going to do with orthogonal projection later on. Okay, so we take a linear combination of vectors, C1, U1, C2, U2, all the way out to CP, UP, and we dot it with some other vector. How can this be rewritten? So if you combine the fact that you can distribute vectors to the sum of two vectors, and you use that along with this vector that involves scalar multiplication and dotting, you can write this as C1 U1.W plus C2 U2.W all the way out to CP UP.W. So that's going to be useful when we go soon to prove the formula for orthogonal projection, which we covered like at the beginning of multivariable. You may remember it, right? That proj u sub v or whatever. We're going to go back and prove that again, and that's going to be useful to this least squares thing we're going to study. Okay, easy so far, everything you've seen before. All right, length. So length is defined by if v is the vector that's got all these scalars in it, it's made up of a bunch of real numbers, then it's just defined as the square root of v1 squared plus v2 squared all the way out to vn squared. That's length. That's magnitude. What's wrong?
I forgot about this.
Yeah. So that's really just if we're in 3 space or 2 space, it's like Pythagorean theorem, but in n space, that's all called magnitude. And a vector whose length is 1 is called a unit vector. And if we divide a non-zero vector v by its length or multiply by 1 over its length, we obtain a unit vector. This process is sometimes called normalizing v, and we say that u is in the same direction as v. So if v is some vector and we want to make it unit length, we can either make it longer or shorter by just multiplying it by 1 over its length and turn it into a unit vector. That's going to be important when we talk about orthonormal sets in a few days. Okay, distance, we talked about this in multivariable as well. So how do we compute the distance between two vectors? We just take the magnitude of u minus v, or we take the magnitude of v minus u. Okay, so length between two vectors is going to be important because, well, here's where we're headed. Let me draw you a sketch here. We're going to take a subspace, W, and we're going to take a vector that's not in that subspace, and we're going to ask, what is the vector that lies in W that is closest to Y? In other words, can you find the vector in here? And of course we can. We know this from multivariable. The vector is going to be this Y hat, which is the projection of Y onto W. So we have to have an understanding of how does this work? We've already done it for a lower dimensional case. We've projected vectors onto other vectors. How do you project vectors onto subspaces? And that allows us to solve an unsolvable linear system using some of these methods. Okay, so visually, here's what's going on, right? You've got U here and V here. If you take U and one copy of negative V, right? So we're seeking this distance right here. This is what we want to find. Let's draw a copy of negative V off on the tip of U. So here is a decent copy of negative V. And then if you go from beginning to end, you start here at the origin and head out to here. This vector is the vector u minus v, and its magnitude is the same as this one up here, right? That's the same as u minus v. And so if we're interested in the distance between two vectors, we can just subtract them and then find the magnitude. That's our distance. This is just by this parallelogram thing. And do you guys remember which part is u plus v? Which part of the diagram?
Just be like
The diagonal of the parallelogram. Yeah.
Oh, yeah, you could do
So
that.
once you create a parallelogram, like, you know, it would be like that distance right there. Or no, would it be? Yeah, that would be right. That would be right. Yep. Okay, so that's distance. And we did that in multivariable as well. Too fast? Are we okay? Go on to the next page. Question? Good? Okay. All right. So find the distance between 1, 2, and negative 3, 3. So let's compute u minus v. So u minus v is 1 minus negative 3, or 4, and 2 minus 3, negative 1. And then we'll find the magnitude of u minus v, and that is the square root of 16 plus 1. So the distance between those two vectors is root 17.
Right? Yeah, it's better.
Why is what?
You're using 2 lines for magnitude. Usually.
You know what? I think that's because our textbook uses that notation now.
You will never recommend another. I know this one.
Sure.
Now,
He's the staller, that's right. By solving for y, since it was the easiest variable, and I treated x and z like the free variables, right? So it's like x and z are both input variables here, and then y was the one that was constrained. You could solve for any of the variables, and you'd get two vectors that span w. Question? No? Okay. So what this means is that every vector in W is orthogonal to the basis for W perp. You all recognize how I got that? Remember A, B, and C from the plane equation? Remember how the normal vector to the plane equation is A, B, and C? So the basis for W perp is just the coefficients of the plane. So let's take a linear combination of the things in W and make sure that it is indeed orthogonal to the basis of W perp. All right? So we'll take another weird combination like 8 times the first vector, which is a 3 by 1. Oops, that's not a 3 by 1, sorry. So 8 times the vector 1, 2, 0, minus 6 times the vector negative 3, 0, 2. And this vector should be orthogonal to anything in W perp. So let's dot it. Oh, you guys.
I don't know if you meant it.
I didn't mean it to be, yeah. So answer, comma, Now I'm going to just take a scalar of the thing I said W perp was. So we'll just take 2, negative 4, 6. This should be 0. We're good. Okay? So that means any vector in W is orthogonal to any vector in W perp. Those two subspaces are orthogonal. Any vector in W is orthogonal to any vector in W perp.
Oh.
Yeah, that should make sense.
Explain how you got the W.
Perp. Yep. So really what we're trying to do is we're trying to say once we have these two basis vectors, we're trying to basically solve x dot v1 equals 0 and solve x dot v2 equals 0. We're trying to find the set of vectors when dotted with the basis vectors that gives us 0. But in effect, what you're doing is just finding the normal vector to the plane, which is the coefficients of the plane, remember? ABC, remember? 2, negative 1, 3, that's how I got them. But just so you're okay with this, if I solve that, x dot v1 equals 0 and x dot v2 equals 0, we should still get that 2, negative 3, negative 1, 3. Let me show you that. That's actually kind of interesting. If I solve the dot product of 1, 2, 0, comma, x, y, z. Oh, shoot, those are stored as something. Let's copy and then start a new document. Okay, so we're going to have the dot product set equal to 0 and the dot product of two other vectors set equal to 0. This is negative 3, 0, 2, and x, y, z. That means the solution is a scalar multiple of the vector 2, negative 1, 3, which is exactly what W perp basis is, right? So don't lose sight of the fact that we're actually doing this, because if we get out of the simplicity of R3, that's going to be really important for us to understand. In other words, what this is saying is we seek all vectors orthogonal to the basis vectors of W. And we can solve a system to figure that out. It would just be more interesting if we were in R4 or R5 or something.
That's how like the other like the calc effects will try to like derive the.
Yeah, I think you're right.
cross-product.
I think you're right. Yep. Okay, two useful facts. One of them is that a vector x is in W perp if and only if it is orthogonal to every vector in a set that spans W. A vector x is in W perp if and only if it is orthogonal to every vector in a set that spans W. A basis, we kind of just showed that. And then the second fact is that W perp is also a subspace of Rn. So not only is the original subspace a subspace, but the new one, the orthogonal complement is as well. Okay, one theorem and then we're finished. The back just has, this is just a fact that we have from Calc 3, from multivariable. We proved it back then, so we're not going to prove it again. Just know it and be familiar with it. So we'll just state and prove this theorem and then we'll be finished. And I'm a little behind on time, but I'm trying. Okay, so let A be an m by n matrix. The orthogonal complement of the row space of A. We've not talked about row space much, right? But consider A to have a bunch of rows which are each members of what? Wait, are there m of them or x of them? Or I mean n of them? M, yeah, there are m, right? Because this matrix is an m by n. So all of the Ri's are members of Rn.
Where did the RJ? Isn't it I columns and J rows?
No. I by J. I is the rows, J is the columns.
Oh,
Yeah.
okay.
Yeah, sorry.
Row space of A is just the column space of the transpose of A, right?
Yes, sir. That's correct. Okay, so that's right. So when I use this notation, you know how we use like call A for column space? If I say row A, that just means the span of the rows. Jaden, did you have a question?
Oh,
Good. Okay, so this says that the orthogonal complement of the row space of A is the null space of A. So here, let's write that out in notation. The orthogonal complement of row A is equal to null A. We're going to try and prove that. Okay? And the orthogonal complement of the column space of A is the null space of A transpose. So call A, its orthogonal complement is the null space of A transpose. Keep those symbols straight. Orthogonal complement on the left, transpose on the right. Okay? So let's try and explain why this is true. So let's consider the equation AX equals 0, which is what we're trying to solve when we're talking about a null space of A, right? Okay. Well, any vector that works here is a member of null A. Does that make sense to you, right? If we are solving that equation, AX equals 0, by definition of what null A is, any vectors that work in there are members of null A. And what I'm claiming is that that whole set is the orthogonal complement of the row space. Let's explore why that's true. Taking A like I've written it and writing it as dot x equals the 0 vector, because that's what we're trying to solve, implies that R1 dot x equals 0, because think about matrix multiplication, remember? We dot a row with a column to get an element of the answer. Remember, the 0 vector is just a bunch of real zeros in a vector, right? So R1 dot x is 0, and R2 dot x is 0, all the way down to Rm dot x equals 0. And look what we have. The set of rows are the very thing that are orthogonal to those x's that work as the null space. Do you see how just writing that out sort of proves it? This shows that like the set of rows and their linear combinations, of course, right? Are the things orthogonal to x. In other words, they're the things orthogonal to the stuff that makes AX equals 0 true. So just by viewing matrix multiplication as dotting rows with columns, you get this evidence that like all those rows dotted with any vector that satisfies that is going to be 0, meaning they're orthogonal. Okay, now let's try and prove the second part of it, that the column space orthogonal complement is the null space of A transpose. Okay, the row space of A transpose is equal to the column space of A, because rows become columns, right? And by the theorem that we just proved, the row space of a matrix, its orthogonal complement, is the null space of the matrix itself, which in this case is A transpose. I've gotten lost in the proof. Hang on. The row space of A transpose is equal to the column space of A.
Well, the row space.
The orthogonal complement of the row space.
Just put it and call it.
Yeah, it's gonna call it for row A transpose.
You just did it, right?
Oh yeah, you're right. It's done. Just put in call A for here. The orthogonal complement of call A is the null space of A transpose. Thank you.
Expecting it to be longer.
Yeah, I was expecting it to be more meaningful than that. I was like, no, that's it, actually. You're just doing a quick substitution. Yeah. Okay? That's all in this section. Okay? If you want to practice any of this and just get a few problems under your belt, I have an assignment on, what's it called? My math lab, my lab math, whatever it is. Yeah. It is not required, and I will not judge you if you don't do it, but just please do recognize this material is covered on the final. Okay? You're free for the next 23 minutes.
Why am I getting an imaginary frequency?